My name is Jonathan Foote, and I'm here to talk about securing C code that seems to work just fine. I'm a principal security architect at this company, Fastly. So I've been there for a couple years, and I'm going to talk about Fastly and use it as an example throughout the talk just because it's where I currently work. But I've had exposure to C code that seems to work just fine in high growth and optimistic environments throughout my career, working as a consultant. Before that, working as a security research lead at SEI at the Carnegie Mellon University, and before that as a software engineer at a big engineering company. So to jump right into using Fastly as an example, Fastly is a high growth tech startup. So it started off as something called a content delivery network. And so what that means is when the company was starting, they went and they put these like small and mid-sized server clusters all over the globe. They call them points of presence or POPs. And they were using kind of a crazy architecture. So they were using low-cost SSDs, low-cost networking gear as opposed to like the big iron that's really expensive. They were using these Arista switches that ran the Linux kernel. And so they're doing some crazy stuff, and it worked. So the company started to grow quickly. They were getting customers even faster than they expected. And as the company grew, this is a common story, they started to add more features. At this point, they call it an edge cloud because there's so many features, running in these points of presence around the globe. They started to have more types of customers, so big customers, small customers, from a lot of different countries. And of course, as the company grew, there were more and more engineers committing code. And this is kind of the story of Fastly, but it's a pretty common pattern for high growth tech startups. I mean, it's a good thing. I'm thankful for it. I have a job, so that's cool. And it's thanks, in large part, to this idea of optimism. So the dictionary says that optimism is hopefulness and confidence about the future or successful outcome of something. The guy in the background here is Dr. Daniel Kahneman. He wrote a book back in 2011 that dealt with optimism and a whole bunch of other topics. And he won the Nobel Prize, actually, for economic sciences back in the early 2000s. And so this is a quote from his book. I'm just going to read it. Optimistic individuals play a disproportionate role in shaping our lives. Their decisions make a difference. They are the inventors, the entrepreneurs, the political and military leaders. They got to where they are by seeking challenges and taking risks. So optimists play a big role in our lives. Some other interesting insights from his book. Basically, he found, looking at scientific studies, some of which he was involved in, that entrepreneurs have more optimism than average. And to go along with inventors and leaders and so forth. So startups tend to be more optimistic organizations. And one thing I thought that was interesting here from his book as well is that optimists inspire optimism in others. And I think it's really important in high growth startups for this to hold, because in order for high growth startups to grow, they take venture capital or investment money. And in order for that to work, the investors have to think, hey, that might actually pan out. I should give them my money. And optimism helps carry that forward. And on the technical side, I think that holds as well, like in staffing. So if you're an engineer looking for a job, you have to think, wow, that seems cool. That seems like that could pan out. I want to go work there. And so optimism is really integral to high growth startups succeeding. And the other point I thought was interesting here was that Dr. Kahneman found that optimism actually provides some advantages over fully rational thinking in some cases. So like fully rational thinking is weighing in the costs and benefits carefully, but actually optimism wins out in some cases. And one of the reasons that is because optimism provides resilience. So when you fail, optimists tend to persevere. Okay, so these are some non-controversial ideas about high growth startups. Basically, how they operate is they tend to take risks, try to do something crazy, kind of like Fastly did, and hopefully it pans out for the high growth startup, but sometimes they fail and they need to persevere through those failures. So that's how they operate. They take risks, they make mistakes sometimes, and then they kind of persevere through them. And so now I'm going to subtly segue to talking about the C language, to change gears a little bit. So jumping back to using Fastly as an example, when the company was bootstrapping, they started putting these small and mid-sized server clusters all over the globe, and more customers started to use them. One of the key engineering trade-offs in implementing and operating an edge technology is this trade-off. There's an inherent trade-off between performance and isolation. So you can think these are small and mid-sized server clusters around the globe. They're serving hundreds, thousands, tens of thousands, hundreds of thousands of customers' web traffic. And so they need to scale, but then also every customer that's running there, they have to feel like they're the only one in that location. And so, dealing with this trade-off is one of the things that comes up a lot when you're working in edge technology. And Fastly, like a lot of other companies in this space, started to deploy high-performance proxies and servers in these server clusters. And these high-performance proxies and servers are often written in C, just as they are in many other places. C is a language that you go to frequently when you're trying to deal with these tight engineering constraints. So what makes C code special? So I'm going to talk a little bit about C and the history and stuff like that to kind of lead up to what makes it both interesting from a security standpoint and also why it can satisfy these engineering constraints. So C was invented in the 1970s as part of implementing the Unix operating system. It was based on this language B, which was typeless, which kind of shows through a little bit. And I was searching for some text about the spirit of C. So like I searched the web and I came across this, I was looking for text from this book, The Rationale for C, and I came across this 1988 copy of PC Magazine. So like in the late 80s and early 90s when they were publishing this book, C was really taking off, they also kind of marketed it in this magazine. And I just wanted to show the cover of that because it gives you an idea of what the environment was like. Like the community was super psyched about 25 megahertz processors being widely available. So this is what the world was like kind of when C was coming of age. So regardless, this is some text from that book, The Rationale for C. And it kind of sums up what C is all about. So I'm going to read a little bit of it. Some of the facets of the spirit of C can be summarized in phrases like trust the programmer, don't prevent the programmer from doing what needs to be done, keep the language small and simple, provide only one way to do an operation, make it fast, even if it is not guaranteed to be portable. And so while C was kind of invented in the 70s and came of age in the 80s and 90s, it remains a super popular language. So this is a snapshot of the TOBE survey of popular languages or language popularity. It's a pretty good reference for this sort of thing. And you can see C is in the number 2 position, and it's been there for 15 years and counting. So it remains a very popular language, and for good reason. It's a very powerful language. It's really versatile, and it's ubiquitous. So most operating systems have support for C. Whoops, excuse me. Okay, so one of the ways that you can shoot yourself in the foot with C is this idea of undefined behavior. So undefined behavior occurs when a C program executes code that is not defined by the language standards. And so at that point, the program is allowed to continue execution. And so what this means is any properties around security and safety, kind of all bets are off. And as an example of when this went awry, back in 2015, Joshua Drake, who's a security researcher, found a vulnerability in this media parser called stage fright. I'm sure people have heard of it. What happened basically was an attacker could send a crafted media file to an Android device and then own it. So in the case of an MMS message, an attacker could send it to a victim. Victim didn't need to take any action. They could take control of the handset and then potentially send it to all of the victim's contacts in this kind of worm. And so it was a really kind of like catastrophic failure. Everyone was in an uproar, and it was a problem. So to look down at what happened in the code here, if you check out line 10, you can see that this buffer is getting allocated on the heap. And this value chunk size gets added to size. Well, it turns out the chunk size is controlled by the input file. It can be controlled by the attacker. And so what can happen here is if chunk size is large enough, it kind of overflows the range of values that are valid for the type, and integer overflow occurs, which is a kind of undefined behavior. So if an attacker supplies a large chunk size, the integer wraps around and the buffer that it gets allocated winds up being really small. And so then if you look down on line 12, data, which is also controlled by the attacker, gets copied into that small buffer. So then heap buffer overflow can occur, can be exploited to get code execution. And then with some privilege escalation, you can own the handset. And so this was a pretty catastrophic failure, and it's pretty subtle. When you're thinking about the volume of C code you have to deal with, it's hard to catch this sort of thing. And so as a testament to how difficult it is to get this sort of stuff right, here was the first patch that went out. So if you check out line 10, you can see a developer added a check to try to make sure that chunk size is reasonable, but it is also susceptible to undefined behavior, unfortunately. So if chunk size is really big, it's going to wrap around, integer wraparound is going to occur, the check is going to pass, then execution will proceed to line 13, and basically the same thing will happen again. So it's hard to get right. And there's some really good write-ups on this online. This one is from the Google Project Zero blog, which I think is worth checking out. So anyway, the upshot here is that very subtle issues in C can cause catastrophic security failures. And of course, this is just one example of many that have happened over the years. So if we put together this idea of high-growth startups taking risks, making some mistakes, and then trying to persevere through them with what happens with C code, basically what we can conclude is that high-growth startups that use C take risks, but then they're going to make catastrophic security mistakes, and then they're just doomed to failure. And I would make a joke about my talk ending here, because that's all there is to it, but we're short on time. So obviously this is not the case. But there are some unique challenges to securing C in a high-growth environment, in an optimistic environment. The good news is that there are a lot of useful C tools out there. One of the cool things is because C has been around for so long, there's a really mature ecosystem of tools. There's actually a bunch of really good curated lists of tools online too. I listed a few on the slide. You can Google for them. There's a bunch more. I wanted to make a note here, like if you work in application security, you probably talk to a lot of vendors. And in some cases, it's difficult to find vendor tools that actually solve your security problems. But in the C space, there actually are some really good, robust ones out there. Like if you've ever tried to write a static analyzer against Clang, it's possible. You have to write some C++ code. You have to compile Clang with debug symbols probably. And you can do it. It takes some time. It's even harder to get developers to do it. But meanwhile, if you go to certain vendors, you can find static analysis tools that have a UI for defining rules and refining them and stuff. So there's some good ones out there. But there are also some really great open source tools, and I wanted to call one out here. So one really useful tool is this thing called Clang, which is a front end for the LLVM compiler. So Clang supplies a framework for a whole bunch of useful security tools, and what you see here is an example of something called undefined behavior sanitizer. And I called it out here because this addresses undefined behavior, which is one of the reasons that stage fright came to pass. So if you check out the code in the before section, you can see integer addition, kind of like we saw in the vulnerability. And of course, wraparound can occur and undefined behavior can manifest itself. What UBSAN effectively does is it adds a check before the addition occurs to see if the undefined behavior is going to occur, and if it does, it's just going to exit. It's going to error out and give you a useful backtrace. So the upshot here is that Clang provides a common integration framework for a growing number of security tools. And of course, there are a ton of good open source tools out there. But I think Clang, if you think about the amount of time that you have, to deal with security issues in a high-growth startup, it's worth considering from a strategic investment standpoint. It provides a really, if you have your project building with Clang, you can add certain compiler flags, certain linker flags, maybe link in another library, and you get a new security tool. So there's a whole bunch of tools in there, and they tend to be on the bleeding edge of usable security, which is nice. So at Fastly, for example, this has been a really big win for us. So this is an example of a project at Fastly where we build production versions of it with GCC because we've done a ton of performance optimization to make sure it runs super fast in production. But at the same time, we also, as part of our CI process, we build it with Clang, we build it with a whole bunch of different sanitizers. And so as an example of this working out for us at Fastly, you can't merge a PR without building both with GCC and Clang and passing this big battery of integration tests. So it's really saved us a ton of pain on the security engineering team, but also just on the development and SRE teams at Fastly. So this has been a big win for us. And I recommend, if you're thinking in terms of investment of your time, it's worth checking out Clang. So I keep using this word investment, and I think it's important when you're in a high-growth environment, in an optimistic environment, to really think about all of the security controls in your SDLC as investments. Because once you put something in place as a gate your developers have to go through, you basically have to support it indefinitely. And when you have very finite resources and a lot of competing priorities, it's important to really be choiceful in what you're going to, choosy in what you're going to implement and roll out. And so one of the kind of problems with using a traditional SDLC in a high growth environment or a DevOps environment is that it isn't always a perfect fit. So, the older SDLCs, they've been updated, but they were kind of originally based on this idea of a box product model where you build something, you secure it, you build it, you secure it, and then you ship it. And when you're in a DevOps world, code is shipping almost all the time. So the idea of doing a final security review or fuzzing before releasing doesn't really make sense. And so in response to this need, coincidentally, in response to this need, the Slack team, Lane Ari in particular, started to publicize this idea of a self-service SDL. And so the idea is you build kind of automated tools for your developers to use as part of the SDL so that they don't block on security and it frees up time for you. So the developers are less frustrated, you have more time to build other services and so forth. And we thought it was a pretty cool idea. So Fastly, Lane Ari were nice enough to spend some time with us and describe how they did it. We actually implemented something like you see here. This is a self-service risk assessment. Brian Adaloy, who's the AppSec lead at Fastly, built something like this for us. And we thought this works really this works really well. And it has really helped us kind of keep our hands around risk at Fastly. So we thought it was a pretty cool strategy. But the truth is, at a high growth tech startup, there is like a massive volume of stuff you have to do. So this chart is just the 50 most recently used repos at Fastly. I just charted the number of PRs over time, and you can see it's kind of an exponential growth. So there's a ton of code flowing in. In addition to like code flowing in, there's also a bunch of new tech. So people are using new frameworks, they're using new languages. So it's enough to keep you super busy. And of course, it's hard to find good AppSec engineers that can both do application security work, they can do specialized work like C, and then also build security services. It's just a hard thing to do. And so, this is enough to keep an AppSec team extremely busy. So one of the things that's actually going on kind of inside all that code that's flying through your pipeline, it often is this idea of a minimum viable product approach. And I don't know if this is like the most modern term. I'm a little out of date on process stuff. But the idea is that developers are often kind of like building something, just enough of it to see if it's going to work, and then they ship it, and then they try to gather feedback to see if they can iterate on it or if they should just drop the project altogether. And so they're trying to collect the maximum amount of validated learning from their customers as they can with the least effort. And so it's kind of a process of develop, ship, learn, and then iterate. And so at Fastly, for example, like on the AppSec team, when we were like, just getting barraged with a lot of work to do and kind of, dealing with new technologies and things like that. And we also knew that we wanted to build self-service security for C projects, but we just didn't know, how do we make time to make that investment? And so eventually it had dawned on us that like, well, we can kind of use that tool for ourselves. So we could try to use an MVP approach for automating security services. And so I'm going to talk about an example of doing that here in just a minute. I'm going to talk about doing it for this thing called continuous fuzzing, and I'm going to give a little background on fuzzing to start, and then maybe tell a story. So this is not a talk on fuzzing. You could do many talks on fuzzing. Hopefully this is just enough fuzzing to understand what's going on here. So fuzzing in a nutshell is you start a program or reset its state, you feed some random input to it, and then you look for misbehavior. So often in the case of a program written in C, you're looking for a crash, and it works really well. That's basically why it's so popular. Code that behaves well under fuzzing is usually code that's already been fuzzed. So to tell a little story about this, back in 2015, shortly after I joined Fastly, I was trying to figure out a way to expand fuzzer coverage inside some of our server code bases, and I read about this experimental feature in American Fuzzy Lop, which is an awesome fuzzer, called persistent mode. And I figured out how to apply it to the server code bases, and I was doing it on my own time, so I tested it out against Bind, which is this ubiquitous DNS server, and I almost immediately found a critical vulnerability. And we were phasing Bind out at Fastly, but that's the code base I wanted to work on. And so I found this critical vulnerability. I worked with the vendor to coordinate disclosure. They took my fuzzing patch, started to fuzz their own stuff, found their own vulns. Other security researchers started to find vulns and work with the vendor to disclose them. And so it's like, this is going awesome. I had these ideas. I was talking to my buddies. I'm like, we're going to fuzz all these other code bases. This is going to be really, really powerful. But then I got really busy, and I just kind of stopped doing it. And I'd be lying if I said this wasn't the first time I did this in my career, where I would go really gung-ho about fuzzing and then kind of run out of energy. And I don't think I'm alone. So across my career, I've seen a lot of instances of this. It's what I call heroic fuzzing. Someone gets inspired to do fuzzing. It could be a security engineer or a researcher. Maybe they found a new technique like I did, or a new code base or something like that, or attack surface. Then they fuzz it until they find bugs, which almost inevitably happens. They work on fixing the vulns, and they're going to fuzz less interesting code paths in the program, and maybe expand to other code bases. But then eventually they get busy, and the fuzzing stops for whatever reason. Maybe the box they were fuzzing on, they'd use it for something else, or the upstream developers change the code base so that your fuzz harness doesn't compile anymore, and never get back to it. And I want to mention that like, while this happens, a lot and it's not perfect, you don't really get security assurance over time, it is a really good thing that fuzzing happened at all. But it is a problem. You don't get security assurance over time. And so in response to this, the team at Google kind of pioneered this idea of continuous fuzzing. And so the idea is that project developers really own the fuzzing integrations. They're the ones that are writing the integrations. You always target those fuzzers against like the latest or release candidate version of the project, and you run them continuously on dedicated infrastructure, beefy infrastructure like a cluster or something like that. The bugs get reported back to the developers, and that way security can really focus on providing a good integration framework and running the infrastructure and also supporting developers. And so this solves a lot of the problems with heroic fuzzing kind of intuitively. One interesting note here is that because fuzzers you're empowering developers to write fuzzers, you can potentially require them to build them as part of the SDLC, which is something we do sometimes at Fastly. So this is definitely a best practice. There's this awesome project called OSS Fuzz out there. If you're using OSS, I would recommend checking it out. You get Google. The team has been really great to work with, and they give you a lot of compute resources for fuzzing. But then the question is, what do you do for continuous fuzzing in private repos? And so this is what we were working on at Fastly. Basically, our focus was an MVP approach, and we really knew that getting something usable was the really hard part. Like I've actually built fuzzing clusters before in my life. It's actually really fun. But getting something that developers would use, it was the hard part. So we were really focused on that. And so what we ended up doing was really leveraging OSS Fuzz. We basically copied their program and hacked some of the bits to make a fuzzing cluster. We ran into a few problems though. The three main problems were that we needed to access private repos, we needed to maintain progress between the fuzz runs, and then we also knew that we weren't going to have as much automation as the OSS Fuzz team did. And so we kind of addressed these in an intuitive fashion. Because we were still running this thing manually, we knew that we could just forward an SSH agent in, just like you would if you were cloning a private repo as a developer. So we did that. We hacked the OSS Fuzz code base to maintain progress between fuzz runs. And then, of course, to this day, actually, I log into the fuzz server on a daily basis and make sure it's not on fire. And of course, I look for crashes and stuff like that. And so I like the Wizard of Oz analogy, pay no attention to the man behind the curtain. So this worked well for us at Fastly. We've found, high and critical impact bugs and caught some of them before they go into production. We've also, one cool thing that happened was in our public integration for H2O, which is an HTTP2 server. The NG HTTP2 team took our seed files and used it to find bugs in their project, which I thought was cool. And also our internal continuous fuzzing server has been a pretty useful proving ground for testing out fuzzer integrations. So I don't want to give the impression in any way that this is done at Fastly. We started out with training earlier, working with developers to understand if it would work for them. We had some labs, some of them went well, some of them didn't go so well. But it really was kind of, it's a continuing effort. It's not done, but we are finding high and critical impact bugs, and it's working for us. So I think it was a worthwhile endeavor. So it did address our resource constraints, to some extent, but of course, it didn't solve our problem completely. So I'm going to talk quickly about this idea of server security, which I think is another important component to securing C code, in a high-growth, optimistic environment. So traditionally in AppSec, and throughout my talk at least, I've really been focused on code. But what we're really interested in is code that runs on infrastructure that's operated by engineers in some environment. So the idea here is that the thing we really want to secure is the code in flight, not the code in place, of course. A while back, I came across this paper by this guy, Dr. Cook, who is an expert on medical device safety, on medical system safety. And he came up with this idea that, in his paper, he had this idea that people continuously create safety, which I thought was really interesting. The idea is, even if you design something as well as you possibly can, you spent robust SDLC and you try to catch all the bugs, really it's going to fail in the field at some point. Like in his background, like a medical device, like an infusion pump, it's going to fail, and really then you need the operators of the device and the infrastructure that supports them to really create safety for the whole system of interest, for the system in flight. And so if we think of safety as all the things that could go wrong with the system, then we can, malicious or accidental, then we can think of security as a subset of safety. And I think the idea still holds. Really, everyone has to work together to create security. So that includes the security team, developers, your reliability engineers, your customer-facing engineers, and even sometimes your customers and users. We all have to work together to really create security for the C code in flight. And so the reason I mention this is that this is where optimism really shines. To flip back to a quote from Daniel Kahneman, the main benefit of optimism is resilience in the face of setbacks. So this is anecdotal stuff, but like if you work with an optimism bias in proactive measures, it can be difficult in some cases. So you might hear things like, oh, that's a corner case, that probably won't happen. Or the thing's been like that for months or years, it won't get exploited. And this bottom one was a quote from a really good engineer, actually, who I like. He's a friend. But he said, this is talking about a vulnerable service behind a firewall. If that service gets discovered, I'll redact it. So it can be kind of difficult to work with optimism bias and proactive measures, but in reactive measures, it's kind of awesome. So I've seen some really crazy stuff, like really like bulletproof incident handling. So I've seen things like, optimists doing things like they don't shy away from work. So optimists tend not to hesitate to report issues that might make a lot of work for them. So for example, if they're going to report a potential security issue that might end up firing up an incident and costing them their whole day or multiple days, they do it because they want to do the right thing and they follow through. I've also seen some insane security remediation skills like open heart surgery in the back of a moving bus type stuff. Like, of course, at high growth startups in optimistic environments, you tend to have super talented people and their capabilities can really shine in remediation. And then of course, high growth startups tend to skew toward like adrenaline junkies and people that want to do the right things for customers and they really love their brand and they love the people. And so there's usually a relentless commitment to kind of operational resiliency. And so in order to secure C code that seems to work just fine, I think it's really important to support secure operations. So this means teaching your customer-facing and operational engineers to detect and report potential specifically C-related security issues. So for example, at Fastly, we have training where, we talk about what a memory disclosure or memory corruption might look like, how to detect it, how to report it. And we even have an exercise where there's like a fake customer report and you have to use production tools to figure out if it's memory corruption or not. So I think that's a great first step, but I don't think it's enough. I think you also really have to participate in creating security. So that means participating in incident commands and response when security issues are found or when vulnerabilities are found in the field. And to lead it if you can, to really work as part of the team and understand how it's done. And then of course, the last one might be obvious, but I think it's really important to support reporters and incident responders. So it's a key, because C vulnerabilities can lead to like catastrophic failures, in order to detect them, you're probably gonna have tuning so that you get some false positives. And so when people report false positives, you need to support them and say, hey, thank you for reporting that memory disclosure vulnerability. It wasn't an issue, thank you for reporting it. And don't just tell them, but tell their management as well, because it's really important in securing the system in flight. So to sum everything up, there are no real shortcuts. You still have to work toward C security engineering best practices. All the conventional wisdom still applies, even in high growth and optimistic environments. But with that being said, you have to think like an entrepreneur. Everyone around you is working super hard toward their goals, and so you need to work super hard toward yours. Work shoulder to shoulder with them. Do things like try an MVP process. You don't have to stand up a perfect security control, but start with something and iterate. And then finally, it's important, I think, to leverage the strengths of optimism for security. So this means specifically teaching folks what C vulnerabilities and exploitation are going to look like in the field, and then working with them and remediating it. And that was super fast. Thanks everyone very much for your time. I don't know if we have a few minutes for questions. Yeah. Okay, thanks everyone.